Hello everyone and welcome to our video presentation. Today, our group will be exploring a real-world application of basic analytical chemistry that affect us every single day. We will be discussing the use of paper chromatography to analyze and separate synthetic food dyes in everyday consumer products. If we look around the grocery store, the food and beverage industry heavily relies on vibrant colors to make products like candies, syrups, and sports drinks look appealing to consumers. However, these bright colors are often made using synthetic food dyes. Because some synthetic colorants can carry health risks if misused, they are strictly monitored by food safety authorities, such as under our local food regulations 1985, to ensure they are completely non-toxic and safe for us to eat. This is where analytical chemistry comes in. It provides the essential testing methods needed to monitor manufacturing quality and protect public health. To test these consumer products, analytical labs needs a method that is efficient, accurate, and cost-effective. The ideal tool for this is paper chromatography. Chromatography is a physical method of separation where a complex mixture is divided into its individual chemical components. By applying this technique to a sample extracted from a candy shell or a sports drink, we can physically pull apart the blended colors to see exactly which specific dye pigments the manufacturer used. To truly understand how this separation happens, we need to look at the chemical theory behind the two phases involved. If you look at the diagram on the left, you can see our stationary phase, which is the paper stream firmly fixed vertically inside the chamber. On the right, our bullet points highlight that this paper is made of polar cellulose fibers. At the bottom of the chamber is our mobile phase, which is the liquid solvent eluent. The magic happens through the mechanism of differential affinity. As the liquid solvent climbs up the paper via capillary action, the individual pigments inside our food dye begins to react. Pigments with a high solubility in the solvent travel faster and higher up the plate. Meanwhile, the pigments with a strong adsorption to the paper move much slower. This basic chemical relationship is what allows us to see the individual components of the dye separated perfectly.
Now, we are going to talk about the method in chromatography. For step 1, we place a colored candy like a Skittles or M&M in a few drops of water to dissolve the dye. Use a toothpick or capillary tube to place small spot on the extracted food dyes into the pencil line. Now, add 5 milliliter of solvent like water or rubbing alcohol into your beaker. Now, moving to step 2, we must carefully lower the paper into the beaker. We must ensure the solvent level sits below the pencil line and it doesn't wash away your food dye spot. Wash as the solvent travels up the paper, carrying and separating the individual color pigment hidden inside the food dye. And for the last step, remove the paper just before the solvent reaches the very top. Immediately mark the highest point the liquid reach with a pencil line. Now, we measure the distance traveled by the solvent front and each separated food dye pigment to calculate their RF values.
How does chromatography work? Chromatography is used to separate different pigment or color found in the ink and dyes. When the liquid solvent moves off the paper, it carries the pigment with it. However, some pigment dissolve better in the liquid than others. The pigment are more solute will travel the fastest and move furthest up the paper, like the blue spot on the right side of me. Analyzing chromatogram. RF is stand for retention factor. RF values are used to identify unknown chemicals by comparing them to a range reference substance. The RF value for a particular substance will always be the same if the same solvent and stationary phase are used. We can apply my above formula, which is Rf distance travelled by the spot over distance travelled by the solvent by the value of the red spot is 3 over 5 equal to 0.6. We also can visually match an unknown ink sample, again no reference chemical, to see what is made of. On this chart S is our unknown ink sample, and 1, 2, 3, and 4 are the reference chemical. If you look closely at the head of the spot, sample S contain a red spot and a green spot. These line up perfectly with reference chemical 2 and reference chemical 3. Therefore, we know chemical 2 and 3 are present in our ink sample, while chemical 4, 1 and 4 are not.
To wrap everything up, our analysis shows that paper chromatography is both an effective and highly economical method for separating and identifying synthetic dyes in consumer products. While this technique is primarily utilized for qualitative analysis, meaning it helps us visually identify what components are present rather than their exact quantities, it still provides incredibly valuable information about a dye's chemical composition. Because it is simple, low cost, and reliable, it remains an important tool widely used across education, industrial quality control, and preliminary laboratory investigations. And that's all from our group. Thank you.